Now that we have the dot product, we can go on to the best theorem in the whole class. Maybe it's not one we're going to use that often, but it's called the Cauchy-Schwarz inequality. It is used quite a bit in mathematics, and I'm going to show you the proof of it because it's probably my favorite proof of all time. So what the Cauchy-Schwarz inequality says is that if you ever take any two vectors and you dot product them, you get an answer. The absolute value of that is always going to be less than or equal to the product of the individual lengths. Now, you could prove this with the cosine theta thing that we just had in the previous video, because cosine theta is always less than or equal to 1 and greater than or equal to -1. But regardless, that only works when you have a nice theta there, that you know what you're talking about geometrically. And this dot product idea here is going to work even in weird vector spaces. So we're going to do a different proof. Again, I think it's one of the best proofs in all of mathematics. What we're going to do is we're going to just take any vectors here, and I'm just going to say it's an arbitrary vector space V, and I'm going to look at the length of the vector x plus t times y for some number t, and it could be any number here. Now we know that since this is a length, it has to be greater than or equal to 0. Okay, and in fact, if you square it, it has to be greater than or equal to 0, which again doesn't have any problems here. But there is something that we didn't actually look at before. But if you take the length of a single vector and you square it, it turns out to be that's the same as if you dot product it with itself. And you can just work out both sides of the equation here, and it's true. So that means I'm doing the vector x plus ty dot product x plus ty. And then you can actually FOIL using dot product. You may not be aware of that. Now the thing is, x dot x, this is just some number, I'll call it c. X dot y is some number, I'll call it b over 2, just so that when you combine it with a 2 it becomes b. And y dot y is some number, I'll call it a. So what that I can write this is that means I have at squared plus bt plus c is greater than or equal to 0. Now this is a quadratic polynomial in t. And in order for this polynomial to be greater than or equal to 0 no matter what, that means it has to be fully on top of the x-axis. Now if it's fully on top of the x-axis, that means that there are no real solutions. And if there are no real solutions, that means the discriminant is less than or equal to 0. Right? If the discriminant was positive, you'd have two real roots here. Now technically the discriminant can be equal to 0 because we can have a parabola that just barely touches it, because again this could be equal to 0 here, but certainly you can't have two real roots. So what is the discriminant on that? The discriminant is b squared minus 4ac, and we need that to be negative. Oh, but what is b? B is 2 times x dot y minus 4a was y dot y, and c is x dot x. And so then what you're going to see here is you're going to see 4x dot y, move the other term over, 4x dot x, whoops, x dot x, and then y dot y. And then divide out the 4's here. And we get x dot y is less than or equal to, and then x dot x, sorry, this should be squared. And then x dot x is length of x squared, y dot y is length of y squared. Square root both sides, and you finally get the result x dot y is less than or equal to length of x times length of y. And again, this works in any vector space actually, so it's a really slick proof here. With that said, the Cauchy-Schwarz inequality is usually used to prove other theorems. It's not usually used to solve practical problems. So it's very good from a theoretical point of view, but we probably won't do a whole lot with it in this class.